Single-phase motors, some additional types, and some troubleshooting tips. In this presentation, we're going to look at additional types and troubleshooting tips, but specifically for split-phase motors because this is the most common motor out in industry when it comes to single-phase applications. Now, there are other types of single-phase motors out in industry other than the split-phase motor. There are shaded pole, universal, and synchronous reluctance single-phase motors. Split phase being the most common, synchronous reluctance being more of a cutting edge or specialty type of application, or seeing more and more being deployed in renewable energy. So we all know about this one, split phase design, that's the most common. But what about a universal motor? Well, a universal motor is one that works on both AC or DC, and its presentation or manufacturing is almost identical to a DC cumulative compound motor. A shaded pole motor is one that is extremely cheap, extremely low starting torque, and mostly built into equipment, not really something that you as an electrician would install. It's got a single winding, and reversing the polarity of the incoming AC source will not affect the rotational direction of the motor. It's named a shaded pole because of the small metallic ring that is embedded into the face of the magnetic pole itself, right here. By adding that pole, we actually cause a delay, or by adding that ring, we cause a delay in when maximum magnetizing flux will be generated on that portion of the pole face. As the AC sine wave starts to increase, the magnetic strength is going to be greatest on the left side, and due to this ring, there will be a counter EMF that is generated, which will oppose the initial EMF. As we get to the peak value, the entire pole face will now have maximum magnetizing strength, and that's because the current value will no longer be rising. As the current is dropping, the counter EMF induced into this ring will cause a generation or an increase in the magnetic flux density that is right adjacent to the ring. And then the whole thing starts yet again, but in the other polarity. If we take a look at the pole face left to right, it appears as though the magnetic flux intensity is traveling from the left side of the pole face to the right side of the pole face. And what that means is that the rotor inside the motor will then be cut by magnetic lines of flux and pulled along in the direction shown. To reverse the motor rotation, the entire rotor of the motor would need to be removed and reversed. So obviously not easily accomplished. Finally, we have a synchronous reluctance motor, which looks totally cool. There's no rotor winding on this type of motor. It operates at zero slip. It can be manufactured as single or three-phase, and it's being deployed currently in electric vehicles. It has extremely good speed and torque characteristics, and in motors or cars such as the Tesla Model 3, Model S, Model X, all of those use synchronous reluctance motors that look almost identical to this. They do require special controllers in order to operate, and it's not simply a standard 240 volt AC that is applied to them. We don't really go into much depth on this type of motor, as it is mostly being deployed in areas that are manufactured as opposed to something that would be installed by an electrician. When we troubleshoot split phase motors, there's a few things we need to keep in mind. If the start winding is open, the motor will be unable to start, and that's because there will be no phase shift between the run and the start winding. If the motor is unable to start, it will draw a significant current and likely trip an overload or even a breaker. Centrifugal switches will fail over time. They're mechanical linkaged items that are spinning on a shaft. Capacitors will fail open or slowly lose capacitive value over time. If we take a look at a standard split phase motor, there's a few things that we can verify. First, we can verify how many ohms the run winding is, how many ohms the start winding is, and remember that if we have our ohm meter across 5 and 8, OL would indicate a break. And because there's a mechanical device there, most likely a failed centrifugal switch. If I measure 0.2 on my run winding, then I'm assuming that between 5 and 8 is a higher ohmic value. What that value actually is very much dependent on the motor. If I measured OL, that means that there is a break in the winding, or more likely, a damaged centrifugal switch. When the motor is starting, we know that it's going to be the start winding is going to be connected. When it's running, the start winding will be disconnected. And if the centrifugal switch became broken or jammed while the motor is running, it would mean that the motor would continue to run, but would be unable to restart if it was stopped at any time. On the other hand, if the motor is starting and the centrifugal switch is broken or jammed in the closed position, the motor will overheat due to high current being drawn, and it will not be able to reach its rated speed or torque rating. Different types of capacitor-start split-phase motors have a little bit of additional necessary steps that we need to be cognizant of. First, remove cover and check the capacitor farads. Sometimes the wire gets broken between the capacitor and the motor itself, or sometimes you simply need to verify that the farad rating of the capacitor is still what it states on the side of the capacitor itself. So in order to do this, you would need to open the cover and disconnect the capacitor from the motor and connect your meter to it in the farad rating. On the other hand, you might want to confirm that the start winding and the centrifugal switch are in proper operating condition. You can't just put your ohm meter across 5 and 8 because the capacitor isn't open and it will always indicate OL on your meter. So you need to remove the cover, jumper the capacitor out, so connect the wires together without the cap, and check the ohms, T5 and 8. Again, if it states OL now, that tells us that there's a broken start winding or that there's a damaged centrifugal switch. Finally, a capacitor start and run motor will have two different capacitors of different sizes. So don't assume that they should be the same. They will most definitely be different. One is for starting and one is for running, and they will also have different ratings when it comes to their continuous operation. One is short time duty, the other is long time or continuous duty.